Okay, so here's where we left off. We have one more example I want to do for triple integrals. And again, we've made the observation that there's some formalities that ideally could be said about how to make the definition of a triple integral over a non-rectangular domain, and we're not going to go into that. But the big picture idea of triple integrals on non-rectangular domains is just like for rectangular domains, just like it was for double integrals, chop it up, add it up. That's the big point, right? We're taking some domain, we're chopping it into little pieces. Let's not worry about notation. And on each little piece, we're looking at what the answer to our question is. How much accumulating quantity is there on each little piece? We're going to add it all up, right? And a lot of other development that we came to. What we're spending most of our time focusing on here is not how to turn an application into a triple integral. Chop it up, add it up. That's pretty straightforward. The geometrically challenging part is how to turn a triple integral into an iterated integral. And so we did a bunch of examples of that last time of different ways to slice and how to draw the pictures, and there's challenging geometry in triple integrals in that sense. Okay, all right. So one last example that I think is worth doing. So my region D here is bounded by. So remember what that means, right? And there are 5 planes, z equals 0, z equals x, z equals 2 minus x, y equals 0, and y equals 3 minus z. And at a quick glance, this looks like a nightmarish challenge of various planes intersecting in these different ways, and we've got to figure out what this thing looks like. Oh my gosh, how is this even possible? Right? And this would be, if these were 5 random planes, this would be a crazy hard problem. Okay. What we have here, though, is not 5 random planes. And so there's something special about some of these planes that I want to point out. And it allows us a good foot in the door to understand the question. And the special characteristic I want to point out is that these first 3 planes have a very cool feature: no y's. Right? Now let's think back to chapter 1. If you have an equation of a plane, if there's no y's in the equation, so you have ax plus 0y plus cz equals d. Right? Well, that tells you something about the normal vector. It tells you the normal vector does not have a component in that direction, in the y direction. And that tells you, if you think about the geometry, that the plane is parallel to the y-axis. So this is a big deal. So we have 3 planes that right off the bat, chapter 1 argument, right off the bat, these first 3 planes are parallel to the y-axis. And that makes them, I'm going to say easy to draw. In particular, I mean it's easy to draw them in relation to each other. I'm going to draw all 3 of these planes here. Look, these planes are parallel to the y-axis. Z equals x looks like that in the xz plane. Then the plane z equals x is just, that dragged parallel to the y-axis. That's what. Right? Along those same lines, no pun intended. Z equals 2 minus x. Is that what it was? Let's see here. Z equals 2 minus x. Looks like that in the xz plane, dragging it parallel to the y-axis. That's what that second plane looks like. And then z equals 0. Now, of course, that was arguably an easy one in the first place, but looks like that in the xz plane and drag it parallel to the y-axis. So right off the bat, we know we're looking at the first 3 planes anyway. We're looking at this kind of triangular cylinder. I guess you could call it a prism. Right? So our first 3 planes make a prism. So in order to figure out what our solid looks like, all I've got to now do is figure out how do the other 2 planes intersect this cylinder. And these other 2 planes, not that bad. Y equals 0. All right. Y equals 0. How does that plane y equals 0 intersect our prism? Well, like that. So we're sort of chopping it. If you were taking that prism and making a vertical chop on it and cutting off one side. Okay. The last plane, y equals 3 minus z. Now this one's a little. I'm going to have to think this one through. No x's, you'll notice. Right? So this plane, y equals 3 minus z, parallel to the x-axis. So we're going to be making a cut through this prism parallel to the x-axis. Let's look at it in the yz plane. Y plus z is equal to 3. In the yz plane, it's something like that. Drag that parallel to the x-axis. Something like that. Now think about how that plane, we've got this prism here, and then we've got this plane that's cutting it kind of at an angle like this, right? And how does that, it's just going to make a sort of a sloping down sort of cut. It's not a vertical cut like that first one, like that green slice. We're going to take an angled slice through this prism, and it's going to slice through something kind of like that. And so altogether then, our solid is that thing there, which I have a better picture of here. So there's that solid. It is not that rare to have situations like this come up where the way you're going to identify what your solid looks like in the first place that question of identifying what your solid looks like in the first place is actually non-trivial. That is part of the question here, to figure out what it looks like, right? And this strategy of kind of looking at it a little bit at a time, and then look at some of your bounding planes first, and then look at the other bounding planes after. That strategy can be a really good one. So, for your consideration. All right, now the next thing I want to do is talk about how to slice. What order should we put our differentials? This one, it turns out it matters a lot which way we slice. So let's think about some options. We'll start with this option of doing our x slicing first. Our x slices look kind of like that. Right now, let me recognize, you got to really be able to visualize what this solid looks like and think it through, and have good geometric sense to of what does this thing look like, and then as I slice it, what do those slices look like? And so that's another sort of, there's a challenging aspect of the problem that is just the 3D visualizing part of it. So, okay, is there anything wrong with those kinds of slices? And not for the first few that I drew, but you'll notice that for larger values of x, for greater values of x, the slices are importantly different. For these slices over here, larger values of x, it is the sort of, I'll say, this face that determines the upper bounds on z, whereas for the original slices, it's this face back here that determines the upper bounds on z. Right. Said differently, we sliced through a corner, well, more like an edge, but nevertheless, we sliced through something where bounds could jump from one face to another face. And that means that if you put your dx on the outside, right, if you do your dx slicing first, and then, it doesn't really even matter what order you put the other differentials. Because you do your dx slicing first, you're going to have to break this up into two separate integrals. At least. And that doesn't even comment on, what happens further through the process. Which turns out to be fine. But still, anyway, let's not do this, right? There's going to be more effort to do this with two integrals. Let's see if we can find a way to slice that would only involve one. Wouldn't that be nice? Okay. So let's try slicing perpendicular to the y-axis first. So our y slices, well, they look like this, which is all well and good until you get to that corner. Don't slice through the corner, because look at what happens after that corner. Your slice is qualitatively different, right? And so that's going to be a problem as well. So you're going to have to break this. If you were to do your dy slicing on the outside, like so, dy there, and then it doesn't even really matter what order you do the others. Somehow or another, there's going to be problems, and you're going to have to break up this into two separate integrals with dy on the outside. So again, pass, right? Let's not do that. Let's call it Plan B anyway. I mean, we certainly don't want to do that. If there is a way to do this without having to break it up into multiple pieces, that would be great. So now let's try last shot. Let's try our Z slicing first. The Z slices all look like this. No problem. They all look the same. Bounds all in the same faces. No issue. Right, so this is the move. This is definitely what you want to do in this case. You want to do your DZ slicing first. DZ on the outside, and then, by the way, now moving along to, on a given Z slice, do you want to do your X slicing first, or do you want to do your Y slicing first? In this case, it kind of doesn't matter, because you'll notice that this is a rectangle in here, and so you take your pick. So Z slicing first is super convenient. I will point out, if it had been a slightly different solid, if the, let me redraw now to make a different solid. Let's suppose that this plane were not parallel to the x-axis, as in this case it was. Let's consider, what if it were something more like this? And let's get rid of, let's see how I'm going to try to erase all of this. Hide it with white pencil marks. Okay, so with our now modified solid here, right? Now, which way should we do it? Should we do, or should our second slices be dx or dy? Well, let's look at our existing z slices. Our z slices now look like that. That's not a rectangle. And if you think through the different options, if we were to do our dy slices next, our y slices would look like this until I hit this corner, and then I'd have a problem. So doing dy next would be a bad choice. So again, let's not do that. Let's instead do our our x slices first. Everything's fine and dandy. So I suggest that dx would be next, and then whatever. Go ahead and do your dy last. Everybody see the reasoning there? Very happy. Okay. Now again, that's if we had this modified solid. If there were a different fifth plane, cutting at a more awkward angle, as it is. With this solid, doesn't matter. As long as you do Z first, you're good. Okay. All right. The rest of the details are here in the book, Finding These Bounds. I want to encourage you all to think through those details on your own. Again, it's all in the book here. Okay. All right. So, moving along, we're going to take a change of, kind of a change of theme for the next several lectures. We have been developing different kinds of integrals and talking about applications of integrals, definitions, and then how to compute those integrals sort of directly. Double integrals, triple integrals. Okay. We're going to now slightly change gears and talk about techniques, more so techniques of integration as opposed to new integrals. Right? Now, that said, we are going to define a bunch more integrals. I think I counted through one time. We're going to have a grand total of like 9 different kinds of integrals in this class. And so we have plenty more to come. But for the moment, I want to talk about some techniques. The first one's called change of variables. It is part of a general strategy involving this problem. What if your domain is undesirable? right? And we've seen the domain can be very undesirable. Depending on the domain, that's kind of the challenging part of computing a triple integral, is finding out how to take your domain, ugly as it is, and how do you slice it, and what are the corresponding bounds. That can be hard. So if you have an undesirable domain, is there a way to rewrite the integral over a different domain? Wouldn't that be nice? We could just say, you know what, I don't like that domain. I like this nice, pretty domain over here. I mean, it almost seems too good to be true, right? Turns out there's a way to do this, and you got to be careful. And there's asterisks involved, right? There's a little cost you have to pay, but nevertheless, we are going to be able to take an integral defined on one domain and rewrite it as an integral defined on a completely different domain. It's awesome. Okay. In fact, I will point out, y'all have already seen an example of this. Now, you didn't think about it that way at the time, but it's the substitution rule from single variable calculus. Y'all remember the substitution rule? Here it is. You probably don't think of it in these terms. People tend to think of the substitution rule as, look, if I say x equals g of t, then come on, dx equals g prime of t dt, and so that's that. And let's see. And then let's see. Oh, this is this, and that's just kind of what it is. Right? We've thought of this in the past as being an algebraic tool, and in fact, it served mostly an algebraic purpose. In the past, why would we bother doing substitutions? It's because one side or the other of this equals sign, I don't know how to find the antiderivative. Substitutions are a way to help you find antiderivatives. Well, we're going to use something like substitutions as a way of changing the domain. And by the way, notice, when you change, if you're looking at t going from A to B, t goes from A to B, then that means that x goes from g of A to g of B. That's what the equation says. And you can write out explicitly what these antiderivatives are and confirm that this is what works. So again, not having even thought about it in those terms, we've seen a tool that turns an integral on one domain into an integral on a different domain. And by the way, go either way you want. Whichever way, it doesn't matter. Okay. All right. So now, as I've done on many occasions, I'm going to take a tool of single variable calculus. I'm going to look at it in a different way. The goal in mind being not to solidify your understanding of single variable calculus particularly, but if we look at this single variable calculus from the right way, then we get a launching point from which we can do multivariable calculus in the way that I think is easiest to see it. So I'm gonna study now the substitution rule in single variable calculus for a couple minutes. And first thing I want to do is I want to think of this a little bit more geometrically. X equals g of t. Let's not just think of that as an algebraic sort of tool for let's stick this in there algebraically. Geometrically, we have here a function, g. The input variable is t, the output variable is x. Let's draw that picture. We have a function, right? T goes in, x comes out. The interval from A to B on the t-axis, its image is the interval from g of A to g of B on the x-axis. So I want to think of this literally as the function g is picking up stuff that's over here, and it is then depositing it over here. Okay. All right. Which, by the way, results in, you can kind of see how that would connect anyway, with these bounds being different and in the way that they are. Okay. All right, now a little bit more precisely. Let's look at this interval from A to B over here. Let's chop it up into little pieces, as of course we often do. And now let me point out that each one of those little slice points, I can plug all those points into this function g, and out comes a slicing of this interval on the x-axis. Now it's not going to be an even slicing. It's going to be all kind of irregular. Right? The first thing I want to observe, now this is just, I think this is a very reasonable appeal, right? But when we've defined integrals in the past, I acknowledge, confess, yes, we've defined integrals with regular slicings. B minus a over n, right? Every delta x is always the same for each piece. But I appeal, that doesn't really matter. If you think about it, if you're interested in computing the, some amount of mass or something that's on that axis, chop it up, add it up, does not really hinge on those pieces being the same size. The total mass is still the total mass, right? So I'm going to make the observation that if I were to use this new slicing over here as the way to slice up this interval on the x-axis, I could think of that as resulting in a Riemann sum. I could think of that as a way to compute an integral on the x-axis. Okay. All right. Okay, so let's talk about these pieces then. We've got this little piece over here of size delta t, and it has an image, which is a little piece over here of size, I'm going to call it delta x, and I added a bit of subscript of 3 because, well, over here, these delta x's are not all the same size, so I'm calling it delta x sub 3. Okay. And I ask, what is the relationship between these sizes? And I'm going to think of it specifically in how much bigger is the slice on the x-axis. I want to think of it along those lines as how much do I stretch that little green subinterval? When I take that green subinterval and pick it up and set it down over here, it's got to get stretched out by some amount. How much does it get stretched out? And I claim we already have a tool for answering that question. Instead of thinking of this as a piece of the t-axis, let me reinterpret that as representing a change. That represents t starting there, ending there. T changes by a certain amount. And this process of t changing by a certain amount results in x changing by a certain amount. And we know how to relate input changes to output changes. That's the derivative. Right? So the relationship that I propose between delta x and delta t is that the factor that you multiply by how much it gets stretched out, I like to call the stretching factor. This interval gets stretched by a factor which is g prime. Okay. All right. So delta x is g prime times delta t. And we're basically there at this point. Let me walk you through the algebra. If I have an integral on the x-axis, so starting with it, and let me come back up here for a second. If I have an integral on the x-axis, starting here, if I want to rewrite all of that stuff, everything in the x integral, if I want to rewrite it all as an integral on the t-axis, we have all the tools that we need. There it is as a Riemann sum. X is g of t. We just agreed here that delta x is g prime delta t. There's that stretching factor. This is what I like to call the stretching factor here, how much the little piece of the domain gets stretched out. And now we're just going to kind of move parentheses around. I mean, in fact, notice that everything in here, everything in that expression right there is all written in terms of t. We started off with an integral on the x-axis. And we have an expression that's exclusively in terms of t. And so again, moving parentheses. If I just kind of take those parentheses away and remove the parentheses like that, check it out. I've got a Riemann sum on the t-axis. I have an integral with respect to t. This is integral of that function dt. And there's your substitution rule. Yeah, let's see here. I've got to switch to the right. Here you go, your substitution rule. Okay, so we started off with this integral, right? And we did some algebraic rewrites, and our result was this integral. Okay. Now, two things I want to observe that I think are important. In the past, you've probably thought of this thing here as being a consequence of the chain rule. And that's fine, it's true, yeah, sure, fine, right, from a, depending on how you want to look at it. Algebraically, you can think of this as a consequence of the chain rule. I want to take you a new point of view on this factor here now. That factor now, that is what I want to think of as a stretching factor. That's how much you have to stretch out a piece of the t-axis to give you what it turns into on the x-axis. So stretching factor, I think it's a very natural way to think about it. So I don't want to say forget about the chain rule, but when we're doing this kind of thing going forward, you should think of that less about the chain rule and more as a statement about how stretching of pieces of the domain. Okay. The other point of view I want you to take on this, and now going back to our picture. Back to our picture here. Oh, hang on. Going back to our picture, notice what happened. We started with an integral defined on the x-axis. Right, the integral, we had integral of f of x dx. Right. That integral, after we kind of plugged in what we know about how x's come from t's, the effect was that we kind of turned that integral into, an integral over here on the t-axis. Integral from a to b, let's see, f of g of t, g prime, but all this business here. Right? Specifically, and what I'm trying to draw your attention to is it looks like we moved backwards. Right? We turned the purple integral, that's what we started with, and we rewrote the purple integral as the green integral. Now what's weird is the function goes to the right, what we're calling the substitution function goes to the right, but the integral transforms to the left. Now, that's just because that's how plugging in works. Right? We have a formula that gives us x in terms of t. If you plug in, then all the x's turn into expressions involving t's. So there's not a particularly deep point here, but nevertheless it's something that has to be observed. And so this is, like I say, it's a consequence of how algebra works, but plugging in, and I'm going to say now further than that, the substitution process pulls the integral backwards through the substitution function. And so we call this a pullback. And it's like I say, it's a very natural consequence of how plugging in works. It's not a deep point. Nevertheless, it is something you got to kind of think through. So the pullback strategy is going to be a big point. We're gonna see that in other contexts going forward in this course. So look going forward for other pullbacks. Images can be pulled back through the function. And like I say, the other big takeaway here is the stretching factor point of view. Stretching factor point of view on that factor g prime. Okay, all right. Now let's try to do the same thing in 2 dimensions now. Let's suppose we have an undesirable domain like this one. Now, for a quick observation, let's take a moment to recognize how undesirable this domain is. That would be a terrible domain to have to deal with kind of brute force, right? It's strict. If you come straight at it, you'd slice like that, and then hit a corner. Then you'd hit a corner there, and you'd hit a corner there. And so you'd have to, if you did your dy slicing first, you would have to break this up into 4 separate pieces. And wow, highly undesirable. So you say, let's slice it the other way. Okay, well, yeah, but then, oh man, 1, 2. Don't forget about that little piece sticking out there. 3, 4. Again, going X slicing first, still 4 pieces. So this domain is a bummer, right? Okay. Wouldn't it be nice if we could change to a different domain? And I'm going to use, again, just the ideas that we just did with substitution. I'm going to follow the path. Oh, I got to, sorry, let me go back to the picture here. Step 1, if you want to pull back the integral, is you've got to figure out how you can view your domain as being an image of the new domain that you want to pull back to. Right? Your undesirable domain that you would like to get rid of needs to be the image. Okay, so let's do that. Now, there's details to worry about here. How do you find this function? And yes, right, that can be a problem. And for the moment, I don't want to get dragged down by that point. I'm going to, for the moment, assume that function is given. And we will return to the question of how do you make our domain the image of something? We will talk about that. And side note, it's not always doable. It's not always easy. But for the moment, let's just take that as given. Okay, so our undesirable domain is an image. It's an image of something more desirable, such as, and let's take a best case scenario, such as a nice pretty little rectangle here. And again, this is everyone's favorite domain for a double integral because the bounds are constant. It's just nothing to it, right? That's an awesome domain for a double integral. Okay. All right. Well, if I were to chop up this domain into little pieces, then correspondingly, right, I mean, as I do chops there and there, right, correspondingly there would be chops over here. They'd be curved and bent per the G function, and then likewise chops like that. Would have sort of curved chops over there. Roughly speaking, though, what's going to happen is a little rectangular piece is going to turn into a, well, I'm going to say roughly parallelogram piece over here. These are not going to be the same size. The big question, what's the area of that piece in comparison to the area of that piece? Said differently, how much does G stretch? What is the stretching factor by which areas in the UV plane get made bigger, greater areas over in the XY plane? We got to figure out that stretching factor. And once we have the stretching factor, pull back the integral by plugging in, and everything just falls into place. Okay. All right. So I'm going to compute this area. It's going to turn out to be a multiple of that area. See how that plays out. Okay, how am I going to compute this area? Well, that area, being as it is a parallelogram, that area is something I can compute by understanding these edge vectors. This picture is really small and hard to deal with, so let's look at a bigger picture. I just wanted to blow that up larger to make the picture easier to deal with. Here's that same area. This is the area in the XY plane. And I just want to compute the area of that parallelogram. Well, how do we compute areas of parallelograms? Chapter 1. Right, we got to find these edge vectors and make a matrix, take a determinant. Right, so flashbacks to chapter 1. Is everybody on board with me so far? Yes, question.
How do we know that it's parallel?
Yeah, that's right. So this is just an appeal. It comes from the fact that the way things change over here comes out of the derivative transformation, right? Derivative transformations are linear transformations, and linear transformations just distort things in a uniform fashion, right? So you're right. There's something to be done there, and I don't want to get bogged down in that detail. It's a great question. Thank you for that question, but I'm going to sort of take that as for granted here. Yeah. Right. And it's not exactly a parallelogram. It's just really close to a parallelogram. But again, in the limit, round-off errors are going to go away. Okay. Right. Okay, so I need to determine these edge vectors. This vector, well, it's an image of this vector. That vector is easy to write down. That's E1 delta U. Oh, by the way, I forgot to comment. We're starting off in the x, y plane, and our variables there are x and y. When we do the pullback, our pullback variables, I'm going to use u and v. No particular reason. It's fairly standard. It's common. I shouldn't say standard. It's a common choice. But anyway, we're going to use u and v. Okay, so u and v are our pullback variables. And therefore, this length is delta u. It's in the E1 direction, so it is E1 delta u. Okay. E1 delta u, plug that into the derivative transformation, and you get that output edge vector derivative transformation on E1 delta u. Okay. All right. Now, a little bit of Chapter 3 stuff. What does a derivative do here? First of all, scalars factor out. And second of all, derivative transformations on standard basis vectors are partial derivatives. Okay. Everybody happy? Okay. Likewise, if you look at this second sort of side, if you will, of our rectangle, it's going to have an image, which is the second side of our parallelogram. And again, it's a matter of plugging into the derivative transformation. The derivative transformation applies, and again, scalars factor out, and standard basis vectors go to partial derivatives. Okay, so it's all over but the shouting at this point. I just kind of have to put all the pieces together. But I know these two edge vectors. Those two edge vectors are GU delta U, GV delta V. Let's determine the area by making a determinant. This area is this determinant. That determinant, now, where we compute a determinant, you can multiply, etc. I'd like to point out that both of the factors will have a delta U in them, and let's just pull out that delta U. Both of the factors will have a delta V in them. Let's pull out the delta V. If you don't believe me, don't trust me on this, go ahead and multiply that out. Brute force. AD minus BC. And what you'll notice is that, as I say, both terms have a delta U and both terms have a delta V. They just factor right out. Okay. And we are kind of done. Our output area in the XY plane we now see as a factor times the input area, the rectangular input area in the UV plane, and that stretching factor is the absolute value of the determinant of the Jacobian matrix. You just got to remember that formula going forward. Okay, how are we doing? Questions? Everybody good? Okay, so here then is your change of variables formula. This is what I wanted. Here we go. Change of variables formula. So you'll see here the stretching factor. That's how much area in the UV plane gets stretched out to become area in the XY plane. X and Y are g of uv. There's our premise of we have this change of variables function g that takes u's and v's to x's and y's. Everything else is just a matter of kind of recopying. And there you go. So, nice punchline then. If you have an integral over some domain R, view it as an image, and you can turn that into an integral with a new domain D, whatever your pullback domain is. We have successfully, as we were hoping, pulled back the integral that was defined on this ugly domain. We have pulled it back through the change of variables function. We have pulled it back to an integral on our nice, more desirable pullback, pre-image, you might say, domain. Okay. Right. Okay, so let's get our hands dirty. Let's do some. No, I'm sorry. I always move too fast. There, one last little detail I want to point out, and this is just a notational choice, but it's really handy. And that is, let's rewrite the determinant of the Jacobian matrix as this. The reason why is if you write down the formula for the Jacobian, what is the Jacobian of G? Well, it's a great big matrix. It's partial of x with respect to u, partial of y with respect to u, partial of x with respect to v, partial of y with respect to v. And notice it is the partial derivatives, all of the partial derivatives of x and y with respect to the different input variables u and v. So, I mean, this notation's kind of plausible, right? I mean, that is just a kind of a shorthand way of saying, yeah, all the partials of the output variables with respect to all of the with respect to all of the input variables. Very convenient. Now, do be careful. This notation here does include taking a determinant, right? Which, okay. But I mean, it's not the craziest thing in the world because this, if I want to think of this as being a number, it is a number. I can't just set that equal to the Jacobian matrix. The Jacobian's a matrix, not a number. So that doesn't even make sense, right? So anyway, this is the number associated to all these partial derivatives that I need, and so I'm going to use this number-like notation to represent it. So very common choice. I'm a big fan. I'll explain why I'm a big fan after a couple of examples. But anyway, we're going to use that as a notation for that. Okay. All right. One thing that's kind of nice about this notation, you'll notice, this being how the stretching factor is used. Let's rewrite that with differential notation like this. Notice, and again, the hair stands back on the back of my head when I do this, but it's almost like those cancel. Right? Of course, whoa, this is not a fraction. You can't just, that does not make sense. That's not legal. Oh my gosh. Right? But it's somehow really satisfying that what looks kind of plausible is actually true. So that's nice. Okay. All right, now let's get our hands dirty. Do one. Here is a question. I'm going to consider this domain here. That domain is what you get out of this function applied to the unit square in the UV plane. Now the details. The function is this right here. It's given. Right there. G is a formula. And here I better zoom back in so you can see that. This is the function that does that. Take my word for it. Again, we'll talk about how to find change of variables functions soon, in the next few minutes. But again, just to get our hands dirty so that we can successfully have gone through one, I'm going to say here it's a given. This change of variables function is free for nothing. Okay. And I claim that what that function does is it turns the unit square into that weird purple shape there. Okay. All right, and suppose that you want to do an integral now over this weird purple shape. Specifically, the integral that I want to do on that purple shape is this one. I want to do an integral of x plus y on this crazy domain here. And let's recognize this is a highly undesirable domain. As you slice, you're going to be hitting these corners whichever way you slice. It's going to be 3 separate integrals if you do this directly. So, nobody wants to do that. Okay. All right. So we're going to do a pullback. Again, the pullback setup has kind of been given to us. We've been given what this function is. We've been given the pullback domain is the unit square. We just have to kind of go through the motions now. And the first step, as you'll recall, the first step is to take our change variables function and compute the Jacobian determinant. And don't forget to take the absolute value. We're just going to compute this formula right here. That stretching factor, absolute value, determinant, Jacobian matrix. Okay. Alrighty. Here's how that algebra plays out. So there's our formula. The Jacobian is this. Now you got to take some appropriate partial derivatives, right? Don't forget this is what x is. Right? Your change of variables function tells you what x and y are as functions of u and v. And likewise, this is what y is. So you take those partials with respect to u and v, you get that. Again, make sure you can do it helps to have some muscle memory, intellectual muscle memory on how to do those calculations, so think that through explicitly. You take the determinant and you get this, and now we have an awkward point to deal with. That's an absolute value. How do we deal with those absolute values? And again, very often in high schools, they'll just let's just forget about it. Let's just pretend that didn't happen, and let's just go ahead. Right? Wildly inappropriate. Of course, you can't do that. Now, let's worry about this. How do we deal with these absolute values? Okay. Well, we're going to figure out how to deal with the absolute values by looking at these expressions themselves. There's u and v right there. What do I know about u and v? And it turns out we actually know a lot of information about u and v. You can see it right in this picture. U and v, u is always between 0 and 1 on the domain that we're interested in. Right? And likewise, v is always also, as it turns out, also between 0 and 1. So this expression here, this can be all over the place if we didn't know about u and v, but we do. U and v are between 0 and 1, and that means that can never be bigger than 4. And that means that this will always be negative. We're taking the absolute value of something that is always negative on the entire pullback domain that we're interested in. And the absolute value of something that is negative is its own negative. Hope everybody's comfortable with that. Now again, I know that high schools are really bad about absolute values and inequalities, and high schools like to stick around and talk about equations because everything's nice and clean and works well, right? But so if you are if you have had a deprived background on dealing with absolute values and inequalities and this kind of thing, square roots, commonly ignored and underdeveloped. Come to my office hours, we'll straighten it all out. Okay. All right. Okay. All right. So there's our stretching factor. And here we go. Dx dy, stretching factor times du dv. We just computed this stretching factor there. Yeah. Now, what do we do about the x and the y? What do I do with x? Don't forget, the change of variables function tells you what x is. X is just that. Right? And likewise, the change of variables function tells you what y is. Y is that. Everybody on board? So we've done the pullback. Everything is now written in terms of u and v. In the integrand, we have an integral du dv. This is full stop, an integral in the uv plane at this point. We have pulled it all the way back, and we get to use our much more desirable pullback domain, unit square, bounds are constants, good constants no less, and life is good. Right on board? Okay. All right. Okay, here's a different one. Now this one, I'm going to show you how to find a change of variables function. In this case, I emphasize finding a change of variables function. It's not an algorithmic process. It's not always do this, or the function will always be found inside of the following. No, it's going to be different for every problem, and sometimes it's not tractable, and you have to be kind of head on a swivel looking for opportunities to find your change of variables function. Here's an example that works sometimes. Our domain is a square with these 4 vertices. So that's this. We're given that it's a square. Of course, it's not hard to directly confirm. If you know the 4 points, you can just find the edge vectors and take the dot products and the magnitudes, and it's easy to confirm this is a square. Okay. All right, but we're given that information. And now I ask, what is it that's undesirable about this domain? What's undesirable is that I'm going to hit corners. Like if I'm slicing like this, I'm going to hit that corner, and likewise going the other way, the other corners. You might say what's bad about this domain is not that it's a square, but that it's tilted awkwardly. So how am I going to view a tilted square as an image of a square that doesn't have that annoying feature of being tilted? Well, I'm going to view it as being literally a tilting of an untilted square. If I take that and if I just tilt it, right, there's my change of variables function. It's just, my change of variables function is the process of tilting by some angle yet to be determined counterclockwise. That counterclockwise rotation turns the green square into the blue square. Yeah? Okay. All right. Okay, now details. What is that angle? What's the angle theta here? How much is everything getting rotated? I can tell that by looking. I can see that theta right here, actually. There's theta. So you can look at the coordinates of that point and do some corresponding trig, and this ends up being pi over 6. And I'll remind you, trig is prerequisite to this course. I'm going to assume that you are proficient, quick, reliable, accurate with trig. So our change of variables function is just a rotation by the angle of pi over 6, and that's easy to write down. This is basically an exercise from chapter 3. Chapter 3 on linear transformations. Okay. So, all right. So there's your change of variables function. I should say that's the matrix representing it. Here is the actual change of variables function, written as as a function of u and v. Proceed, compute the Jacobian Determinant. Good news, the Jacobian Determinant turns out to be 1. Bit of good luck there. How nice. Let me recognize it's not that surprising. Right? I mean, if you think about it, stretching factor of a rotation, well, it's a rotation. It's a rigid motion. Nothing gets stretched. That's actually pretty geometrically clear. Right? So this is not surprising. Now, that said, I do still want to see, even if there's a geometric argument for why your stretching factor ought to be something obvious like 1 or something like that. Still, give me the algebra on an exam. But nevertheless, I think it's satisfying that it worked out to be something expected. Okay. And then, off to the races. Plug and chug. Our stretching factor, you can see right there. This stretching factor is that 1. X and Y are functions of u and v in the usual way. X is the first part of the change of variables function, and so that goes there. Don't forget to square it. Y is the second part of the change of variables function, so Y goes there. Don't forget to square it. All algebraic downhill algebra from here, and you end up with that integral. Okay, which on a rectangle, which is easy to compute. Okay, next example. This is a tricky, weird one, but this is tricky and weird in a way that's surprisingly common. By the way, this example it's kind of a classic example, but it's also very physical. And just so you know where I got it from, I modified to avoid some annoyances, but this is basically stolen out of a calculation that I had to do as a physics major way back when, taking a thermodynamics class, computing the efficiency of the Carnot cycle, the Carnot engine. So it was very interesting physics, by the way. It's deep stuff. It's very, very cool. But anyway, you find yourself needing to compute with this domain, as it turns out. Or a domain very much like this. Again, annoyances removed. This domain is defined by looking at these two hyperbolas here. By the way, some of y'all might, apparently this has been removed from high school algebra curricula, but these equations, xy equals a constant, are hyperbolas. So, anyway, I think that's worth knowing. Cool fact. And then the other two equations are these. Those are not hyperbolas, but they are, kind of qualitatively not that different. You can see in both of these cases, when x gets bigger, y gets smaller. And so you get roughly the same, qualitatively the same kinds of shapes. But for some, let's point to this. For these, when x gets bigger, y gets smaller. Yeah, sure, right, because the product is constant. But for these, when x gets bigger, y doesn't have to get very much smaller because y gets squared. Right, so y gets smaller at a lower rate, and thus, as x gets bigger, y gets smaller, sort of less so. And then vice versa, over on this side, as y gets bigger, oh my gosh, if y starts getting big and then you square that, x has got to get a lot smaller. Okay. All right. So that's why these curves cross like that, and because they cross, you get this shape that is going to be our domain. And yikes! What an annoying domain. Corners everywhere. Whichever way you slice, it's going to be ugly. So again, pass. Okay. Everybody on board so far? Okay, so here's the change variables function. This is a clever trick. I wish I thought of it. Somebody showed me this before I had a chance. But anyway, somebody showed me this really clever idea. Make your change of variables function go backwards. And now, again, you got to be, you can't just do that and then ignore that you've done something backwards. We are going to have to deal with this, but we're going to define our change of variables function backwards. Being as it is backwards, I'm going to write down a function in terms of x and y. X and y are not my input variables. And I have a very obvious candidate for functions of x and y that should be my components of this h function. The obvious candidates are these functions of x and y whose level sets you're looking at. I mean, they're sitting there. I don't know, make a function out of them, see what happens, right? Maybe we'll get lucky. That's kind of the rationale. Okay. Right, well, okay, so if we do that, let's draw what this undesirable domain turns into. What does it turn into over here in the UV plane? Well, if you think about it, if u is xy, then these curves here become u equals 6 and u equals 10. They become straight lines. How's that? Everybody see the trick there? That's really clever, isn't it? I mean, again, it's the change of variables functions going the wrong way, and we've got to deal with that, and we will. But that said, how about that? Straight lines, very nice. Likewise, because we were clever enough to make xy squared v, these equations becomes v equals 5 and v equals 7. So the domain over here that was between those four curves, it's sort of, well, I have to say image because my function's going the wrong way. But this new domain D over here is a rectangle. And really clever idea. Now, again, this is going backwards, but at least I have the undesirable domain that I'm not interested in. I have a connection to a much nicer domain that I am interested in. Okay, so let's proceed. Let's compute the stretching factor of h. It is a change of variables function. It's going backwards, but it is still a change of variables function. Let's just write down the stretching factor. Think about what to do with that afterwards. But this function, its stretching factor is... well, let me come back up here for a second. That stretching factor is going to be what you multiply by dx dy to get du dv. The function's going this way. This function's going to stretch out dx dy to give you du dv. And that's what I have right here. And ignore that this is not exactly what we want. The stretching factor that I can totally compute stretches out dx dy to give me du dv. Okay. Now let's think about what I want. What I want is to do a pullback the other way. I would like to be able to take dx dy and I would like to be able to rewrite it in terms of u's and v's. I would like to solve for dx dy. And the clever move here is, okay, go ahead. Solve for dx dy. Knock yourself out. This dx dy that you want to solve for, easy to solve for it, just divide, right? And now you have what you can plug in, do your pullback with. You just have to take the reciprocal of the Jacobian determinant. It's a neat idea. And by the way, it's also pretty satisfying if you think of it from sort of a geometric point of view. If h stretches in that direction, we're just looking for how to undo that. And the way you undo a stretch is by squishing. The way you undo a multiplication is by a division. It's pretty plausible. Okay. So you divide by the Jacobian determinant. By the way, this Jacobian determinant is easy to compute, right? X and y as functions of, u and v as functions of x and y. Take your derivatives. Turns out to be exactly v. What are the odds? And plug in. Note that we're dividing, not multiplying, because our function's going the wrong way. Right? We're squishing instead of stretching. And here's your integral in the UV plane over a rectangle. This is a really easy integral. Is everybody on board? Okay. Now let me go back a ways. You'll recall. Oh, that's on that. No, it's over here. Sorry. Going back to way back here. Yeah, this notation for Jacobian determinants. Writing Jacobian determinants as if they're kind of a fraction. And remember, I made the observation that there's going to be something really nice about that. But you should be uncomfortable right off the bat. You should be uncomfortable with the fact that I'm using the notation of a fraction to represent something that is not a fraction. This should be upsetting. A little bit. You should be, hey, whoa, why, you can't do that. should be a little concerned. Okay. Well, here's the thing. Going back to where we just were, we saw that interpreting the pullback, appropriately, dx dy, you have to divide by the stretching factor instead of multiplying because, well, you're going the wrong way, though this is an equation that we used in that development a minute ago. But then let me observe that had we simply done it the right way, if we had simply solved for x and y as functions of u and v and written down the stretching factor, we would have gotten this. So here's the thing. I have now two formulas for getting dx dy in terms of du dv. And therefore, these two factors here are the same. And the nice punchline is that means that this thing here that I've represented as a fraction presumptuously, as if you could just do that, even though it's not a fraction, it's actually a determinant, that thing that I'm representing as a fraction behaves like a fraction because of this observation here. Right? It behaves like a fraction. The reciprocal just flips the numerator and the numerator and the denominator, just like you would kind of hope because of the fraction notation. So that's a pretty strong motivation for writing the Jacobian determinant as a fraction. I think this is super. Big fan. Okay, so strongly encourage you to do that. Another nice thing about it is it helps you keep track in these instances where you're, oh gosh, my function's going the wrong way. Do I multiply? Do I divide? Which way does it go? So easy to get turned around backwards. This notation will keep track of that for you. If you want to know something that you multiply by du dv to get dx dy, well, it's got to behave like a fraction. So I need that to be the numerator, and I need that to be the denominator. So compute whatever is most convenient, whichever one's most convenient. As long as you compute it with the right, as long as you denote it by the correct fraction notation, this will tell you whether what you've computed is something that you multiply or whether it's something that you divide. In either case, the fractional notation keeps track for you of whether you should multiply or divide. That's really nice. Okay. Alrighty. Okay, so we've seen a couple of examples of finding change of variables functions. In this one, if the domain is given to you in such a way that you've got kind of, I want to say, functions of x and y kind of given, right? Notice they have to be functions that are being set equal to constants. Right, so you've got to do whatever algebra is necessary to get, stuff equals constants. But if you have, functions of x and y that are being set equal to constants that define your domain, well, good deal. Those functions are a change of variables function. Backwards and everything. But nevertheless, that's how you find a change of variables function in that case. Rotations is another example. It's different motivation, but nevertheless, that's a way to find a change of variables function. And sometimes, and surprisingly often, this is just the case. That sometimes the change of variables function is actually given. This is not unrepresentative of the real world. Sometimes you understand this function very well, and it is because of what that function is that you need to compute an integral on such a domain. So again, it's sort of sitting there looking at you the whole time. Okay. There's a three-dimensional version of change of variables. I'm going to mostly gloss over this. Y'all can read it. It's just like change of variables in 2 dimensions. The big difference is, of course, we've got a 3-dimensional domain. Can you imagine the nightmare of having to slice this thing up? I shudder to think, oh my gosh, what a horrifying thing, right? We couldn't possibly. But if you can view it as being an image of a nicer domain, we've just got to keep track of, okay, well, that little piece of now volume is going to get stretched out to make this new piece of volume, and I just need to know what's the stretching factor, and then plug it in and pull it back. It's algebra. It's the same thing. The only new thing we have to do is figure out what is the stretching factor from a change of variables function. That calculation is surprisingly similar. We just have to compute not an area, but a volume of a parallelepiped. And volumes of parallelepipeds, you may recall, still determinants. And so hopefully this is no surprise, but that stretching factor is again the determinant of the Jacobian. Details I encourage y'all to read on your own. It's morally the same as what we just talked about. So there's that stretching factor, and having a stretching factor, the volumes get stretched out like that, right, per that algebra. X, Y, and Z are G of U, V, and W. Just plug in your change of variables function, and there you go. You've changed your domain. So, anyway, morally equivalent. Okay, what I want to talk about now is a nice application. Now, we've only got a couple minutes here, but I want to get partway into this. I want to talk about symmetry theorems. I think these are highly unappreciated theorems. So these are a takeoff on a theorem in single variable calculus that I know y'all have all seen before, which is that if you have an integral, an integral here, and if the function is an odd function, if f of negative x is negative of f of x, it's called an odd function. If the function is odd, and if your domain is symmetric, specifically if you're doing an integral from negative some value to positive of that same value, then that integral is 0. No anti-differentiation required, and you just you draw the picture, and of course the picture they draw is often, based on graphs, because, well, it's a single variable calculus thing, and that's, people like to look at graphs. But that function, being as it is odd, let's draw better. Being as it is odd, and again, the people like to talk about, well, this is positive area, this is negative area. And oh my God, no, of course not. There's no such thing as negative area. But these are negative terms in the Riemann sum, and these are positive terms in the Riemann sum. The area is just a tool for measuring how big they are, right? But the Riemann sum terms cancel because they are exactly the same terms with just different minus signs. Okay. All right. Okay, so pretty believable theorem. What's awesome about this is that we computed an integral without anti-differentiating. I didn't have to deal with any substitutions or any integration by parts or partial fractions or no. It's just poof, just gone. Right? Totally cool. All right. Okay, so there are multivariable versions of these theorems, and let's see here. How much time do we have here? Oh gosh. Okay, so let me just give you a context of why I think these are so important, and then we'll start getting into the details next time. Why I think these are so important. Again, past life, way back when. My second major was physics. I took a lot of physics classes. I did a lot of integrals in physics classes. A lot of y'all are engineers. You're going to do a lot of integrals, right? Lots of integrals in your classes. So my estimate, and this is very back of the envelope, and I can't quantify this, I can't justify this, I'll say. But my estimate is about 20%. I think this is a conservative estimate. 20% of the integrals that I did in my physics undergraduate career equal to 0 by symmetry. So these are crazy important. This is one of the most important tools for evaluating integrals that I have ever experienced. It's huge. And like I say, they don't get talked about anywhere near as much as they should, that being the case. So, I mean, if you go through and look at my physics major, I think I looked back at one time, it was 9 physics courses that were required, right? Out of 9 courses, if 20% of the integrals, I can just wave a magic wand and poof, they just disappear. I pretty much just waved a magic wand at 1.8 physics classes. Right? That's impressive. That's a really nice tool to have. So anyway, we will talk about the multivariable version of this theorem next time and proceed from there. See y'all later.